Good morning to one and all. I am Lakshmi Narayanan, an assistant professor in the Department of EC at Dr. NTR Education and Research Institute. So it gives me immense pleasure to present a video lecture on, say, an emerging topic like fundamentals of quantum computers. Say, we have talked about, we have known very well about the classical computing, right? So in case of classical computing, normally we do the process with typical digital data, say logic 0 and logic 1. Logic as just mentioned, right, logic 0 and logic 1. So in a classical computing, it can be actually a discrete 0 or 1. But when it comes to quantum computing, it actually has the inherent capacity of, say, it is, we do not know how much 0 is present or how much 1 is present in a quantum computer, right? So in case of a quantum computer, how much 0 or how much typically comes from the Schrodinger cat story. So Schrodinger is a person who envisaged the concept of quantum computing. Say for example, I tell you with an example of a Schrodinger cat. Say I have a box, a black box, inside which we don't know what is there. If a cat is present and I have a radioactive material along with that, right? So if the radioactive material is inside a small vessel, if it is actually getting emitted, if it gets opened, if it is emitted, what happens is the cat absorbs the radioactive material, it is going to die. We will take the other case. As long as there is no radioactive emission, the cat will survive. So we don't know what is happening inside that box. Either cat may be dead or cat may be alive, right? So same way, quantum computing is actually a combination of a dead cat and a living cat. So we cannot say the cat is dead surely, or we cannot say the cat is alive surely. So same way, so your quantum computing is given by a Schrodinger wave function, which we normally express it as psi. So this psi is normally the Schrodinger wave equation, which is actually being expressed as, say, some alpha into 0 plus beta into 1, where alpha is nothing but the linear operator. So I am just going to express it as a linear combination of 0 and 1. So rather than so how much 0 is present and how much 1 is present is actually depending upon the probabilities. So these alpha and beta measures are coming from your principle of superposition. The parameters associated with principle of superposition, or I can also call it as a linearity principle. So linearity principle means it is actually a linear combination of 0 and 1 rather than being a simple 0 or simple 1, right? Now, so the quantum logic is basically built using quantum gates. And for developing a quantum gate, so one of the important aspect of a quantum gate is a classical gate you cannot reverse it, whereas classical gates are not reversible. So what do you mean by it is not reversible means, say if you convert an input to an output, say for example a 2 input AND gate to a OR gate, output or 2 input OR gate to an output, you cannot take back the input from the output. That is called, if you take back the input from the output, that is called, the process is said to be reversible. So here it is not the case, wherein I have classical gates are not reversible, whereas quantum gates are reversible because it has got equal number of bits at both input and output. Quantum gates are reversible. And one of the basic idea being, say, for a fundamental unit of a quantum computing is a quantum bit, which we shortly call it as qubit. Okay, we shortly call it as qubit. So what do you mean by qubit? A qubit is, as we have told, right? Quantum computing by the Schrodinger cat story. You can have, say, qubit is actually a combination of 0 and 1. So a qubit can be represented as, say, some alpha into 0 plus some beta into 1. This is nothing but your Ket formation of your linear matrix. So a matrix can be represented in two forms. One is graph form and another one is Ket form. Right? So graph form or Ket form is actually your, say, is nothing but your one is a row matrix, another being a column matrix. Right? So this is nothing but your graph form, normally represented as, say, like this, and Ket form, this is nothing but your expression for graph form, and the expression for Ket form will be like this. And when it comes to quantum gates, right? There are fundamentally some important gates that we have. So let us see one by one. First and foremost is so poly X gate is, say, this X gate is being represented as 0, 1. This X gate is represented as 0, 1 and 1, 0. Supposing that I have a quantum state, say, 0, like this, which is being expressed as, say, 1, 0, and another quantum state which is being expressed as, say, 0, 1. Okay. Now coming to our, say, for example, this one. Say if I am going to apply an input qubit to an poly X gate, and here I have an output, right? So what happens is, if I am going to apply, say, for example, let us say for example 0. So what happens is, how you do it actually? 0 is actually where, I mean, 0 is represented as, say, 1, 0 multiplied by I mean 0, 1, 1, 0, right? So it actually, when I am going to multiply, say, this is actually your 0 and this is actually your x, right? So the transpose, this is actually your 1, 0 transpose actually. 0 is nothing but your transpose, this is nothing but your transpose. So you can have it like this, say, transpose means 1, 0, I mean, so it will be 1, 0, 0, 1, 1, 0. What happens is, say, 1 into 0 plus 0 into 1. So it is a 1 by 2 matrix. It is a 2 by 2 matrix. So what happens? What you will be getting is 1 into 0 plus 0 into 1. Similarly, 1 into 1 plus 0 into 0, right? So 1 into 1 plus 0, so first one is 0, second one is 1. So which is nothing but your, so this is nothing but your transpose, means I can rewrite it as say 1 0. Similarly here I can rewrite it as 0 1. Okay. Now coming back to our thing. So when I am going to apply 0 to an x gate, poly x gate, what happens here is it becomes being equal to say 0 and 1. That is nothing but your 1. Now let us see the other case. If 1 is being applied, so 0 is applied, you get 1. Now let us see the other case where I am just applying 1. So if I am going to apply 1, say 1 means what happens, say 0 1. 1 means 0 1 transpose multiplied with 0 1 and 1 0. So what you will be getting is so I will be just writing it as say 0 1. I will be just writing it as 0 1 1 0. So what is your actual 1? So this into this, this into this, and this into this, this into this. Okay. So what you will be getting is say 0 into 0 plus 1 into 1. So it will be 1. Next 1 into 1, 0 into 1, this one, 0 into 1 plus 1 into 0. So it will be getting 0, which is nothing but your 0. So here I will be getting 0. So if you apply 0 qubit to a poly x gate, you will get qubit 1 as an output for a poly x gate. If you give 1 as a qubit, 1 qubit as a input to a poly x gate, you will get qubit 0 as an output gate, right? Now what do you infer from it? Say 0 is being transferred to 1 and 1 is being transferred to 0, right? So what do you mean by it? You get a conventional NOT gate. So it simply looks like a classical NOT gate. So what is the function of a classical NOT gate? It is simply a complement. A classical NOT gate is simply a complement of input gate, right? So what if you give 0, you get 1. If you give 1, you get 0, right? Same way here, we are giving 1 qubit 0, you get qubit 1 as an output. Qubit 1, 0 as an input, you get qubit 1 as an output. If you give qubit 1, you will get 0 as an output. So this is said to be your classical NOT gate, simple NOT gate. Poly X gate is said to be classical NOT gate. So you can also do it as I told you already. Quantum bits are irreversible, right? Or reversible. Classical bits are not irreversible, whereas quantum bits are not irreversible. So say for example in a classical NOT gate, you are giving like this: input, output. So if you are going to provide this output as an input to this pin, here what will happen? You won't get it, right? So what actually is being done here is it is not reversible. You can't get the input from the output that you have obtained. But when it comes to classical C0 gate, it is poly X gate, what happens? You get, say if you apply 1 to a poly X gate, you will get 0, as we have seen just now. If you have applied 0, you get 1. So you are getting back the input what you are giving actually. So the process is right. Process is okay. So one of the important aspect that I forgot to mention is unitary. So quantum bit works on the principle of unitary matrix. Say let U be the matrix. So what do you mean by unitary matrix means? So U into U conjugate will be equal to I. The quantum, the matrix is in such a way that this U conjugate is complex conjugate of matrix U. And if you multiply this U into U conjugate, which satisfies the condition being equal to I, that is identity matrix, only then I can say that it is a unitary matrix. So a condition of being a unitary matrix is an essential one for a QB. And when it comes to say quantum lies in the principle of say superposition and entanglement. There is another one called entanglement. So entanglement of states. So how do you go about entanglement of states? Say for example, I have two things. One is a box like this. Say it is in quantum state alpha 0 plus beta 1. Another one is I have another one having some quantum state. Say alpha dash 0 beta dash. Okay. Now what happens is when you are going to set to be in say entangled state, we will be doing it in say we will be multiplying these two matrices, which we call it as tensor product. So this is nothing but your tensor product of matrix. So if you do it, what happens is say alpha into alpha dash 0 0 plus alpha beta dash 0 1 plus alpha dash beta 1 0 plus beta dash okay. When you are going to multiply this, say a plus b into c plus d, same way you have to multiply. Say ac plus ad plus bc plus bd, same way you have to multiply. So alpha into alpha dash, the tensor product will be say 0 0 plus alpha into beta dash 0 1 plus alpha dash into beta 1 0 plus beta into beta dash 1 1. Now when it comes to say and as we have done it already, so the quantum measurement is based on the measurement of probability. Say how do you go about it actually? Say if any quantum state is being represented as alpha 0 plus beta 1, any quantum state sign is being represented as alpha 0 and beta 1, and what happens is, so it is in quantum state subject to the availability of say alpha square plus beta square being equal to, whenever you take any quantum state, it must satisfy this rule of probability. So probability of a Schwer event is always equal to 1. So whenever it is going to be a combination of say alpha and beta, the magnitude of scaling associated with quantum state 0 and quantum state 1 say is alpha and beta. So its magnitude will be alpha square, and correspondingly for 1 it is beta square. So alpha square plus beta square being equal to 1. And when it comes to say, so whenever I am going to just write this, so if it is of the form, it must be in so when it is of the form, it must be in such a way that these are the magnitudes associated with the quantum states, say 0, 0, 0, 1, 1, 0 and 1, 1 respectively. So what happens is it must satisfy the condition, say alpha, alpha dash the whole square plus alpha beta dash the whole square plus alpha dash beta the whole square plus beta beta dash the whole square must be always equal to 1. Now same way, so you can do it for any number of inputs, say it may be 4 or it may be 8 or it may be 16 and so on. And when it comes to say alpha into alpha dash, so I can typically write it as say 1 by root 2 0 0 plus 1 by root 2 1 1 is a quantum state. It is an entangled quantum state. Say 1 by root 2 0 0 plus 1 by root 2 1 1. It is an entangled quantum state. So it is best being described by the Hadamard gate. So probably 1 by root 2 0 0 plus 1 1, 1 by root 2 0 plus 1, and another one is 1 by root 2 0 minus 1. So on the combination of these two, you can get it as say we'll be getting it as say in other words, if they are having one is being associated with so if I have say 1 by root 2 0 0 1 by 2 sorry 1 by root 2 pardon me, so 1 by 2 1 by 2 0 1 minus 1 by 2 1 0 minus 1 by 2. So what happens is say if at all combinations alpha beta applying alpha beta dash alpha dash alpha alpha dash something like that, getting like this, you can find out just find out these probabilities, say 1 by 2 the whole square plus 1 by 2 the whole square plus 1 by 2 the whole square plus 1 by 2 the whole square. So it is nothing but 4 quarters, that is 1 by 4 plus 1 by 4 plus 1 by 4 plus 1 by 4. This is actually third and fourth term will be minus 1 by 2. So 1 by 4 plus 1 by 4 plus 1 by 4 is actually being equal to. So we can express it provided the squares of the magnitudes associated with each quantum state must sum up to 1. Right? Next, we coming back to quantum gates. Right? We have seen poly X gate. We have two more gates. Say poly Y gate and poly Z gate. poly y gate and poly z gate. So poly y gate is being expressed as poly y gate. So the y gate is being expressed as 0 minus I and 0. So if you are going to express this, apply this over 0 and 1. So 0 is being 0 or 1 is being applied. You can see here I am just applying to your y gate. What you will be getting is, say, if it is 0 actually, let us say for example 0 means 0 1 transpose, right? 1 0 transpose, right? So it will be 1 0 into 0 minus I 0. So what you will be getting is, say, 1 into 0 plus 0 into I. So it will be 0. And another one is second 1 into minus I 0 into 0. So minus I. So which is nothing but your what happens is, so 1 into minus I plus 0 1 into 0 plus 0 into I. So you get first term is 0. Second term is 1 into minus I 0 into 0, you will get, say, minus I into 0 1 if I take. So which is nothing but your minus I into 0 1. Minus I into quantum bit 1. Similarly, if I do it for, say, for example, 1 means, say, 0 1 multiplied with 0 minus I 0. So if I am going to 0 into 0 0, 1 into 1 I, so it will be I. Next is, say, 0 into minus I 1 into 0. So if I take I 1 0, so it will be so it gives out. So if you want to have a complex of its complement, you can use poly y. And when it comes to poly z gate is being expressed as, say, 1 0 0 minus 1. So when I am going to apply 0, what happens? 1 0 1 0 0 minus 1. 1 into 1 0 into 0. So 1 1 into 0 0 into minus 1 0. Next is 1. If I apply 1, for applying 1, so it is 0 1 multiplied with 1 0 0 minus 1. So what you will be getting is 0 into 1 0, 1 into 0 0, 0 into 0 0, 1 into 1 minus 1. So this will be of classical 0 and this will be minus 1. So for a poly Z gate, what happens is, if you apply 0 poly Z gate, what happens is you will get, 0 as it is. So it's actually acts as a buffer. Same input is given. If if you give 1 to a Z gate, poly Z gate, what you will be getting is, you will get -1. That is, you have a phase shifted 180 degree phase shifted cubic. So -1 means it is reversed by an angle of 180 degree. So phase shifted input you will be getting. And when it comes to, say, for example, similarly for a poly Y gate, I can write it as, say, if you give 0, you will get 0 is being transformed to 1, and 1 is being transformed to